Thank you, Holly. Good afternoon to all of you joining us today. My name is Namir. I'm a member of the Timber Design Society Management Committee. We welcome TDS and CSOC members joining us today. TDS welcomes new members to join the society, and you can apply online completing the membership form on www.timberdesign.org.nz, and you will get all the recordings and notices on that membership. TDS is pleased to announce its next couple of webinars, the third in the series of 2021, on 3rd of June by Justin Brown to talk on timber connections with self-tapping screws, and the fourth one in the series on the 1st of July by Lisa Oliver to present an introduction to mass timber posts and beam structures. So stay tuned for further TDS webinars and events coming in this year. Today's TDS second webinar series in 2021 by Dr. Andy Buchanan of PTL Structural and Fire about fire engineering for timber structures. Few housekeeping remarks. Andy will talk for 40 to 45 minutes. Then we'll have questions and answers from the audience for around 15 minutes before the hour when everybody returns back to work. This presentation is recorded and will be kindly made available by Engineer New Zealand soon. Dr. Buchanan is a structural engineer with special interests in timber engineering, fire safety, and earthquake engineering. He is a principal in PTL Structural and Fire in Christchurch. He retired from the University of Canterbury in 2014. Andy has a BE Honours degree from the University of Canterbury in 1970 and a master's degree from the University of California at Berkeley in 1972 and a PhD from the University of British Columbia in Canada in 1984. He is a distinguished Fellow of Engineering New Zealand. Before and after joining the University of Canterbury in 1987, he has been a consulting engineer in private practice, involved in structural design and structural fire design of a wide range of timber buildings around New Zealand and overseas. He is the author of Structural Design and Fire for Fire Safety, John Wiley and Sons in 2017, and the New Zealand Timber Design Guide 2007. He is a past president of the New Zealand Timber Design Society. Please allow me to welcome Dr. Buchanan, and thank you very much for joining us today. Andy, please. Thank you very much.
Well, Namir and Holly, thanks very much. Thanks to the Timber Design Society for inviting me, and welcome to all the listeners and watchers online. So I've been given half an hour or so to tell you everything I know about fire engineering, which is clearly impossible, but I'll do my best. This is really going to be an introduction, in some ways a superficial introduction, first of all to fire engineering. So I'm speaking to people who are not professional fire engineers, I'm going to talk a little bit about fire engineering principles, and then I'm going to move on and discuss how those relate to timber buildings in particular. So let's have a look at the slides. So my first slide is just some photos of timber buildings from the inside, because the fires we're worried about most are on the inside. And what you can see in these photographs here is a whole range of different amounts of wood exposed. In the top right, we can see all the walls and the floors, the exposed wood everywhere. And we move to the top left, and only part of the ceiling's exposed. We move to the bottom left, and we have only the beams and columns exposed, along with some seismic hardware. And on the bottom right, this is a building under construction where the wood was exposed and it's all being covered up with gypboard or something like that during construction. So we have a whole range of different environments, and we'll talk about those. So I have to start off with this curve that many of you have seen before. This is the basics of fire behavior. If we have a fire in a room, if a fire starts in the room where you're sitting right now because the fan in the computer overheats while you're not there, then we have an incipient period while the temperatures are rising. We have some ignition and the fire grows and the temperature rises. There's no numbers on there, but we have a sudden growth in temperature, which we call flashover. And you'll see here on this graph, I've shown two other things. We have what we call the pre-flashover fire, which is the early stage of the fire. And you can see there the sprinklers. And if I turn these sprinklers off and on, if the sprinklers work and they put the fire out, we don't have a flashover. But if we do have if the sprinklers are not there or they don't work, then the temperatures suddenly rise to 1,000 degrees and we have a burning period and what we call the post-flashover fire and a burning period. And once the fuel is all gone, we have a decay period and we eventually have a burnout when the fire burns itself out. So I'm going to say something first of all about pre-flashover fires, and then I'll move on to post-flashover fires, because they're two very different parts of the fire experience. It's in the pre-flashover stage where people will be alerted to the fire, they've got to get out of the fire, that's where detectors and alarm systems will work. If you're still in the building after flashover, if you're still in the room after flashover, you'll be dead because there won't be enough oxygen for you to breathe. So the post-flashover is where we talk about structural fire stability and fire resistance, which I'll move into. Okay, let's say a few words about the pre-flashover fire, which is not of great significance to structural engineers, but it is important. So this is where we're talking about burning items or burning surfaces, and this is when we have time for detection, alarm. The sprinklers will operate. If they're there, the occupants can fight the fire, people can get out, you call the fire brigade. That's the early stage of the fire. And the fire engineers are going to be concerned about fire spreading into places where the fire and smoke spreading into ceilings or cavities or other spaces. And that's part of the passive fire engineering, which I'm not going to talk much more about. The thing that is important, though, in the early stages are the exposed surfaces. And what I'm showing here is a device called a cone calorimeter. This is the cone calorimeter at the University of Canterbury, but all the fire labs have a cone calorimeter, which is just a heating device for heating a surface of something to see how it burns and how much heat is released. And that is one of the methods, not the only method, but one of the methods of testing wood surfaces to see how they behave in fire. And many of you will be aware of the group numbers which we have for exposed surfaces in clause 3.4 of C AS2. And while I'm there, most of you know that that's the CAS2 is the acceptable solution for fire design in Part C of the New Zealand Building Code. And in that clause, we see a table like this, which is a much longer table. I've just shown the top of it for clarity, but that lists the material group number required for buildings with or without a sprinkler system. And there's, in simple terms, we have group numbers 1, 2, and 3. Sometimes there's an S, which indicates a smoke requirement on top of that. But the thing that you need to know about that simply is that normal wood with no protection is in group number 3. So for those categories in the table above, you could not use wood unprotected, but you could buy some or specify some intermescent paint, which would reduce the group number from 3 to 1 or 2, and that is often used. I'm not an expert in that. I would say if you want to know more about that, talk to your fire engineer. And I'm going to move on because we've got a lot more to say. So let's now talk about flashover, which is that time when all the combustible surfaces in the room ignite. Because in the early stages of the fire, there will be some heat and smoke in the room, and there'll be a hot layer growing in the ceiling of the room, and that hot layer will be radiating heat to all the surfaces, and then all of a sudden, flashover is an all of a sudden event when everything ignites like that, and that ignition is going to suck all the oxygen out of the room and produce very high temperatures. And as I said before, you don't want to be there when that happens. So in this post-flashover fire, it's limited mainly by two things, by the amount of fuel available and the ventilation from the windows. If you've got big windows, you can have a short, fast fire. If you've got small windows, you'll have a long, slow fire. And if there is no ventilation, the fire will go out because combustion needs oxygen. Just let's say a few words about sprinklers, because sprinklers are far and away the best thing you can do to provide fire safety in buildings. There's no question about it. Sprinklers are the way to go. And if the sprinklers are there and they work, you won't have any flashover. You have zero fire resistance requirement. That's not what the code says, but that's the reality of it. If the sprinklers extinguish the fire or control the fire, sprinklers won't always put out a fire, but they're designed so that they keep a fire very small, then that's problem solved. Although not completely, because sprinklers are not 100% reliable. How reliable are they? Well, the jury's out on this, but 90%, 95%, 98%. Why not 100%? Well, maybe there's not enough water. And by not enough water, that can happen if too many of the heads are activated all at once, because sprinkler systems are only, the pipe work is only enough to supply a certain number of sprinkler heads. Or if the system is down for maintenance when the fire occurs, or if there's an explosion or an earthquake. We were lucky in Christchurch in the 2010-11 earthquakes, there were almost no fires after the earthquake, but if there had been, there would have been a problem, because most sprinklers rely on water in the street mains, and if there's no water, the sprinklers don't work, and that could be a problem. So this is what we do. The building code says provide fire resistance just in case, even if you have sprinklers. Let's move on. We continue with the post-flashover fire. We have to provide fire resistance. And if you have a fire like this, this is one hell of a fire, as you can see. This is 20 or 30 years ago, and it was a fire in a 2 or 3 story building in Singapore. And the only thing that stopped the whole city from burning down was the fire resistance, which is containing the fire. So the fire walls on the boundaries between that building and the adjacent buildings stop the fire from spreading. In terms of collapse prevention, that did not apply to that building. You can just see the roof there and the flames. If you'd been there 5 minutes later, that would have been gone. But I'm now going to move from a little building like that to a big building like this. And I'll just say a few words about this building. This is the First Interstate Bank building in Los Angeles. And this is way back in, I forget the year, but that's a 62-story building. And that is showing a fire which occurred on the 12th floor. So there were 50 stories above that fire. And if that happens, what do we need? We have to provide fire resistance. What's fire resistance doing? It's doing two things. It has to contain the fire to prevent the fire spreading inside the building or outside the building. There are still people up there. See the lights on the upper floors, and if there are people up there, they have to be protected by prevention of the fire spreading. So fire resistance is initially about preventing the spread of fire horizontally and vertically in buildings. But in addition to that, of course, we have to prevent collapse, because if that building fell over, it would cause a lot of problems. The third thing we have to do, which is sort of a result of providing fire resistance, is to allow people movement so the firefighters can get in and the occupants can get out. And in some cases, there's a fourth thing that we should do, which is to design the building for burnout. In other words, answer the question, what happens after the fire goes out? Because if there's nobody there, or if people leave the building and come back tomorrow, what happens in the meantime? Well, that's often ignored in fire protection engineering, but it's actually very important. Let's move on. Fire resistance. How do we provide fire resistance? Well, the most common way of providing fire resistance is to do a test, a fire resistance test. And there's a furnace that happens to be a Canadian furnace, National Research Council of Canada, but a furnace for doing fire tests of walls. They're all the same. It's a box where gas can be pumped in and ignited, and there'll be ventilation, and there'll be measurement of temperature, and that's what the furnace looks like. So that's the primary method of determining fire resistance. To obtain a fire resistance rating, do a full-size fire resistance test. What do we mean by full size? Well, most testing standards say 3 meters by 3 meters or bigger. Why is it so big? Well, it's that size because you pick up defects in construction and joints and connections which you would not pick up those failures in a smaller furnace. However, there's another way of obtaining fire resistance, and that's by calculation. And we can calculate the fire resistance of lots of things, but it's usually only if that calculation method has been verified by some full-scale fire resistance tests. And that's a Canadian furnace. We have furnaces in New Zealand, Australia, and around the world. And the testing for fire resistance is very similar in all countries around the world. I'll just pop back to that question I raised before about fire spread on surfaces and testing for flame spread and smoke produced. Those tests are different. There are lots of different tests for those, which makes things messy. But when we come to fire resistance testing, the fire test furnaces are similar and the fire test results are similar, and that means that in most cases, if we have a fire test report from Europe or the US or Australia, we can use it in New Zealand because of that similarity. And what I'm showing here is these are the time temperature curves from fire resistance tests. Well, this is for doing the tests, and there are 4 curves on here, but the one we're interested in and the 2 we're interested in just flow up the middle like that. It's It's the International Standards Organization, ISO 834 fire resistance test. And that is the same fire test we use in New Zealand, AS 1530, and it's almost the same as the American test standard, ASTM E119, which you can just see dotted behind it. The top curve for the hydrocarbon fire is not normally used for buildings, it's used for offshore facilities and things like that, and the other lower one's not used much either. The curve we're interested in is that bright red line, which is the standard test fire, and it doesn't matter where in the world you do a fire resistance test, that's the curve that will be used. But in order to pass the test, we have some criteria, and you may have seen this before. What I've got in here are the failure criteria for passing or failing a fire resistance test, and there are three criteria. What we call structural adequacy. It used to be called stability, but that was a misnomer because it's not about instability, it's about structural adequacy. And to pass the structural adequacy simply means that we prevent collapse, carry the load. And integrity, to provide integrity, we have to prevent the spread of fire and smoke, which means that during the test there shall be no gaps or cracks or fissures where fire and smoke can get through locally. And then we have an insulation requirement, which is just measuring the temperature on the unexposed face to stop the fire from spreading. You see some letters in there, REI, and those are used in Europe. Often they'll be talking about the REI values. And then but what you can also see with the X's in that table is that the requirements are different for different things. So if, for example, we have a partition or a fire door, there's no structural, it's not carrying any load, so we don't have to meet the structural adequacy requirement, we just have to meet integrity and insulation. And if we have a fire door or a partition which has a 60-minute rating, it will often be spelled out like this, -60-60, which means 60 minutes for integrity, 60 minutes for insulation, with no rating for structural adequacy. On the other hand, if we have a load-bearing wall or a floor ceiling, in those cases we have to provide structural adequacy and we have to provide the containment function, integrity, insulation, and it'll be 60-60-60, or perhaps 30-30-30 or 90-90-90. For a beam or a column which is only carrying load, it has no containment requirement, it would be 60-, and for the glass in a fire glass in a fire resisting window, it will be 0-60-0. So that's what we're trying to achieve in our fire resistance test. I'm going to talk more about structural fire resistance where we don't have the containment option. But let's move on. What I want to say as well is that standard fire is not a real fire and that everything is different. The photograph on the right there is a fire in a compartment. This was done some years ago at Brands. There's just a box there, a fire compartment, which is about, I think, 2.5 by 3.6 meters, a room size with a facade built there, and you can see huge flames coming out the window. And how hot did it get in here? Well, they're the temperatures. So that different places and different times during that, you can see the temperatures rose very rapidly to 800 degrees and eventually to 1,000 degrees. And down here I have the standard test fire, and you can see that in the early stages of a realistic fire, the temperatures are likely to be much hotter than the standard fire. So what does that mean to the fire engineer? Well, I'm going to come on to it in a minute, but it's all of the fire tests which are referred to for testing walls and floors and penetrations, they all use the standard fire. And so we have to take some account of that if we're going to be using these for a hotter fire. So I'm now, this is just a bit more fire science here. In the building codes around the world, we have something called a parametric fire. And the parametric fire is a calculated fire, a calculated realistic fire, which gives a graph of time versus temperature. And there's two different sets of curves there, because at the top we have the gypsum curves and lower down we have the concrete curves. And those are different because there are three factors that affect the fire resistance, or the fire severity in this case. One is the thermal properties of the building enclosure, and that's why we get, if we have a highly insulating compartment, we get hotter temperatures. If we have a material like concrete which can suck a lot of the heat out and get hot, then the fire temperatures are cooler. And then we have the size of the windows in the fire cell or the fire compartment. And this set of graphs have been just done for one set of window sizes with an opening factor of 0.04, which is a sort of average opening factor. And if we have a fire in this room with a certain amount of fuel load, we'll find that we'll have a time temperature curve that will go up the green line, and when the fuel is all burned out, it won't be quite as sudden as that, but as the fuel is burned out, then we'll have a decay period and the fire will drop. Now, one thing that can happen with our timber buildings is that if we have a lot of wood, exposed wood on the ceilings and the walls, there's more fire load, and if we have more fire load than that, what happens is we jump and push that out to the purple curve, which is the extra fuel, which is coming from whatever source the extra fuel comes from, but it could be in our timber building coming from the walls and surface. And then we go back and we look at the standard curve, and the standard curve, the formula for the standard curve just goes on and on, but there are methods of calculating a time equivalence. And the time equivalence is simply to say that if we know what the real fire looks like, we can say that's equivalent to a longer time of the standard fire, and that is then can be used in lots of ways. So that's all I'm going to say about that now. If you want to know more, do some more reading, but it will help you to get some understanding of where we're going. Okay, let's get started. Why do I say let's get started? Well, just about everything I've told you up till now applies to all buildings, concrete buildings, steel buildings. I now want to start talking specifically about timber buildings and what's different when you have wood in your building. And there are three main things I want to say. The first one is that wood surfaces are combustible. Wood burns. And there are people out there who have various paint-on finishes which will stop wood from burning. They'll tell you that, but for most of them, I would say I don't believe it unless you can prove it. And there is really very little proven material that can stop wood from burning. The intermescent paints we talked about before can stop the surface spread of flame in a building, but once the fire gets out of control, we get into a post-flashover fire. The temperatures are so hot that surface finishes will not stop the wood from charring. So if we're going to stop the wood from charring, we have to cover the wood with something. I'll come on to that later. More than that, if the wood surfaces are exposed, we have to allow for the extra fuel load in that wood. But the best thing we can do is to install sprinklers and solve the problem. I'm going to talk a bit about light timber framing, 2x4 construction, studs and joists, and the strategy there is simple. We protect with plasterboard. I'm then going to talk on some words about heavy timber or mass timber, as it's being called now, where from a structural point of view, we have predictable charring, we have good fire resistance, and we can sort a lot of things out. So let's move on. In the internal surfaces, I just wanted to show you these two slides, these two photographs, because these are some tests done in Switzerland, and two rooms of the same size with the same fuel in the room, but the difference was that the building on the left had exposed wood surfaces and the building on the right had chipboard on everything. And after 7 minutes, this is the size of the flames out the window after 7 minutes. And the building on the left, you can see a huge amount of flaming. And so what's happening here? Well, if we have more fuel and more fuel in the room, then the fire will become ventilation controlled. And when it's ventilation controlled, more of the combustion takes place outside the room than inside because there's not enough oxygen in the room. And that actually can be a good thing inside the room because it means we don't have as much energy released in the room, but it also, on the other hand, it's a bad thing because that can lead to fire spread up the building via the windows. So it makes a difference. And just to give you an example of where this might lead, this is, some people call it the tallest timber building in the world. It's Brock Cobbins at UBC, which has got concrete stair cores and lift shafts. You can see them in the background. And there are 18 stories of wood with CLT floors and glulam columns. And if you go to that building, you don't see any wood at all. This building is fully encapsulated, and all of the wood is protected with 3 layers of chipboard. So if you're going to build in wood, why do you build in wood? Well, the first reason is to see the wood. In this building, you won't see any of it. The second reason is to sequester carbon and avoid the carbon polluting effects of concrete. You get that benefit, doesn't matter how much encapsulation you have, and time and cost. So let's just go back again to this picture. Containment. I want to talk about containing the fire because this is very important. And I've got some photographs here I'm just going to cover briefly, which are looking at some Japanese fire tests nearly 10 years ago now, and the Japanese government sponsored these tests. They were looking at fire safety in schools, and they built a whole school building like this, and they lit a fire deliberately on the ground floor to see what would happen, and you can see below what happened. The building burned down. And there was plenty of fire resistance to the floors and walls, but what was missing was the fire resistant gaps and joins and doors and interfaces. They did the same thing again with a second building, and they managed to contain the fire to 2 floors. They did the same thing again, and eventually they managed to contain the fire to the room of origin. But this cost them $10 million, and what were the problems? Fire spreading outside and inside. So your fire engineer is going to be concerned about this. This is why we provide fire resistance, but we actually have to provide more than fire resistance. This is a fire that occurred in Christchurch 20 years ago, and that is a fire, the photograph taken just as the fire engine arrived, the first fire engine arrived, and it was a fire in an industrial building with a little, I don't know if you can see my mouse or not, but in the front of this building there were some offices, and in here between the fire and the offices was a light timber framed wall. And I went to that building the next day after the fire, and the first thing I saw was out in the main part of the building. That's exactly what we would expect to happen. Those were unprotected steel beams. They got hot, they yielded, they collapsed. This is the concrete masonry wall along the side here, which stayed in place with a bit of delaminating of the face shells. But turning around and looking at this wall, that was the wall, and that was a light timber framed wall which had gypsum plaster on it, and it did its job. And if you go through that door and look at the other side of that wall, that's what it looks like. So light timber framing is fantastic in a fire. It can do its job provided there's enough gypsum there for the duration of the fire. Here's a test at Brands with a fire wall being tested. In most cases, that's all you'll see for the entire duration of the fire. Sometimes you get an integrity failure like this and it actually burns through, very unusual, but it can happen. And in either case, after the fire, when the jib board is taken off, the studs are charred. The fact that you get a 60-minute fire rating for a jib board wall, it doesn't mean no charring. It means that the wall can meet those 3 criteria for 60 minutes. In other words, it can carry the load for 60 minutes, charring or not, and it can stop the fire spread through integrity and insulation. And if you want to know more about that, go talk to Winston Wallboards and look in the jib manual, because all the stuff is there. And if you don't see what you want, talk to Winston's. I'm going to move on to heavy timber. Big glulam beam on the right, an LVL roof lower down. Heavy timber can be large pieces of sawn timber, not very often. More often we're talking about glued laminated timber or laminated veneer lumber, and the new product now is cross-laminated timber, big new panels of cross-laminated timber. And Red Stag are just opening their factory now in Rotorua, and they can make huge panels, 16 metres long and 4 metres wide, and up to 200 millimetres thick, enormous lumps of wood. Question is asked often about adhesives. What's the glue that's used to glue these things together? The traditional adhesive is resorcinol formaldehyde, which is excellent in fire. More often we have melamine products, which are pretty good in fire. The most recent products, including cross-laminated timber, use polyurethane adhesives, and there's a bit of a range there. The standard polyurethane adhesive has some problems in fire, but Henkel, who produced that, now have a new fire-resistant material, and so I'm going to specify fire-resistant adhesive for all of my glued wood products, and we'll just see how that plays out, because what's happened is that the fire-resistant adhesives are now required in North America. If you make cross-laminated timber in the US or Canada, there's a manufacturing standard which requires the fire-resistant adhesive. In Europe and New Zealand, Australia, it's not yet required, but I think we're going to see it being adopted. Watch this space. Okay, I'm going to move on pretty quickly. These are old photographs of buildings in New Zealand which had fires and which were then, the charring was such that the buildings were repaired and reused after the fire. And a timber bridge in Canada, same thing. Here's a fire resistance test at brands of a floor and beams with big loads, applied loads with concrete blocks on the ends. This is not from that test, but what we all know what happens with massive timber in a test is we get charring around the outside, and we can rely on the wood on the inside to provide the fire resistance. We have a new standard, ASNZ 1720 Part 4 2019, which is going to replace the fire chapter of 3603, and that's got some clauses which tell you how the charring rate depends on density, but it says specifically in there for New Zealand grown radiata pine, that's the charring rate, 0.65 millimetres a minute, but we have to also take off a 7 millimetre zero strength layer under the wood. And that's the picture from 1720 Part 4, you can look it up. There's a slower charring rate under jib if we have jib protection. If we have enough jib, there'll be no charring. If it's thinner jib, there'll be some charring, and then a faster rate if it falls off. It's all there. And if we have a massive timber beam like this, we can calculate the charring rate and how much wood is left, and we calculate the residual strength, and we compare the applied load with the residual strength, remembering that we have a reduced load combination for fire, which helps a lot. The wood underneath the char, it does get hot. So eventually, somewhere underneath the pyrolysis zone, we have normal wood. How far down is the normal wood? Well, the char layer's at 300 degrees, but the wood is heated about 30 millimetres below that layer, and there's a graph showing that. I'm not going to dig into that, but that's from my book, Structural Design for Fire Safety. You can see that there. And that wood loses strength at 100 degrees or even less, and that graph there shows the loss of strength of the compression strength, tension strength, shear strength with temperature. So we've got 100% strength at 20 degrees, we've got 0 strength at 300 degrees when it's turned to charcoal, and the reduction, there's a pretty big reduction by 100 degrees, so we need protection. And the wood itself is pretty easy. It's easy to design a beam or a column or a floor for fire resistance using charring. That's simple stuff. Connections, much more difficult. And I just acknowledge David Barber, who's a Canterbury graduate, but Arup Fire, who's helping to write a new document on fire connections. These are his photos. So timber connections in fire, how do you get good fire resistance? You use lots of small fasteners, nails and screws. You bury your plates in the wood so that the steel can't see the fire or the fire can't see the steel. And you use dowels and bolts not so good, but dowels with the dowel heads are hidden. If you have poor fire resistance, well, exposed nail plates, exposed bolted plates, and epoxy. So I'm just going to rush through some photos here. This is what happens in nailed connections. Very poor fire resistance because the steel gets hot and it heats up. You can protect it with jib. You can try intumescent paint, but it's very marginal, very marginal. A nail plate, truss plate like that, hopeless in fire. Screws, much better. They conduct some heat into the wood, but fully threaded screws work well, and that's probably your fastener of choice. A bolt is a problem because the bolt head heats up and the steel plate heats up, and then if the bolts get hot, they cut their way through the wood, like the wood turns into cheese. It's like pushing a knife through the cheese. It just cuts its way through, and so it's all very limited. Epoxied rods, epoxy is hopeless when it gets hot. If you can save it from getting hot, it's fine. But if you have an unprotected connection like this, the steel will get hot very quickly, the rods will get hot very quickly. And there's an old photo of Stu Harris. You're not watching this, are you, today, Stu? That was taken a few years ago, but we've done a lot of work on that. But basically, the problem is that the epoxies are not good for temperatures more than about 50 degrees. If you want to provide good fire protection to a steel connection, bury the steel. Here's some more photos from Arup. So big steel column connection with using this kind of dovetail connection. And what did they do here? They put an intumescent ring around here and then tested it. And after the test, what do you get? The wood's all charred. The intumescent paint has kept the heat out. The connection is at room temperatures. Fantastic. Cover up the wood and hide it. This is another test which Arup did in America for a building called the Framework Building, and they had to get a 2-hour fire rating on this. You see this huge block of wood down here and this beam being dropped in with massive amount of wood protection all around the sides. They did a fire test and a chart on the outside, and they got their 2-hour fire resistance rating. Cover up the wood, it's the way to go. There is a clause in 1720 Part 4 about metal connectors, and it says you can do 3 things. You can embed them like that, or you can protect them and by keeping steel plates to 120 degrees. You need a lot of jib or intumescent paint to do that. In fact, intumescent paint won't do it because intumescent paint doesn't activate till it gets to 200 degrees. So that's not possible, and it says you can protect steel dowels by keeping their temperature to 300 degrees. And so this is actually the hard part of designing a timber structure for fire resistance. The member design is easy. The connection design is not easy. It's hard. And what guidance have we got? The only guidance we've got is this standard, NZS 1720 Part 4, which has been published as a standard, joint standard by Standards New Zealand, not yet adopted by MB. And in fact, the guidance for connectors in there is very weak. It's guidance only at this stage. If you really want to go further, you've got to go back to the Euro codes and see what's there, but it's actually a moving feast. It's changing all the time. Okay, I'm going to stop now. I'm just going to say, if you want more information on this stuff, there's some guidance out there. This NZ Wood Design Guide is only 20 pages. It's a good summary of all this stuff, and that's a free download from the NZ Wood website. Go and have a look at it. If you want more information, this is my textbook, Structural Design for Fire Safety, which I wrote, first published 2001, second edition 2017 with Tony Abu as my co-author. Most of the stuff I've been talking about today is there in the book. There will be an international design guide coming out next year, which I'm working on right now with co-authors in a dozen different countries, including Colleen Wade from Brands and Americans, Canadians, Swiss and Swedish and German people. But if you want to upskill yourself, my best advice is go to the University of Canterbury, enroll in the part-time or full-time, or just take one course in structural fire engineering, because they're the experts and there's lots there. Okay, I'm finished. Thanks very much.
Thanks, Andy. Thank you very much for your thorough and distinguished talk. Really appreciate what you have presented. Very good one. We have a number of questions. I'll start with the most liked ones. People could just like the question just to advance in the list. Number one, when are the new timber design standard being issued?
Okay, well, there's a sort of the new timber design standard is going to be the replacement for NZS 3603. NZS 3603 has been around forever. The last full version was published in 1993 when I was on the code committee. That is going to be republished as NZ AS 1720 Part 1. So it's going to move closer to the Australian standard. It's going to be a New Zealand version of AS 1720 Part 1, and that should have been published a year ago. It's very close to being published, and I'm sure it'll be out by the end of this year. But when it is published, you'll find that there is nothing in it about fire. So in order to get anything about charring rates, you've got to go to the standard I mentioned, which has been published as a standard, ASNZ S 1720 Part 4. Next question.
A question from LDS saying, hi Andy, what are your views on the widespread use of charring calculations for light timber construction? For example, small section timber cavity barrier around 45 mil thick. My understanding is charring rates of 0.65 mil per, it's going in the list, my goodness.
Oh, look, I think I can answer that question.
Yeah,
Thank you very much. If you're thinking about charring of wood, the best way to think about it is to think about a campfire or an open fire at home. If you have small pieces of wood, they burn very quickly. There's lots of surface. It's about the surface to volume ratio. If you have a big log of wood on your fire, it's hard to ignite, and even if it does ignite, it chars slowly from the surface. So, and that's why it does say, I think it says in 3603 in the fire chapter, that the minimum size of the wood for these charring calculations is 90 millimeters. If you have, but that's, let me just say this, that if you have fire stopping and you want to put some blocks of wood in for fire stopping, it's a question of how much of the wood is visible to the fire. If you have a thin piece of wood which is heated on 3 or 4 sides, then you have a problem and you can't use the charring calculation. However, if it's protected so that it's only exposed to one side, then you can use the charring calculation on that one side. I hope that answers the question.
Okay. A question from Debbie Scott. Hi, Andy. Is there a minimum size timber that you can use char rate on? For example, 90 mil? Yeah.
Yeah, hi Debbie. Yes, well, I've almost answered that question just now. 3603 says 90 millimeters. I think the new standard 1720 part 4, I think it says 70 millimeters. But so it's of that order. In other words, if you have a joist that is maybe 45 millimeters, you should not use the charring calculation. But having said that, it actually doesn't matter, because if you have, let's say you have a 45 millimeter wide joist, if you do your charring calculation and you include the 7 millimeter zero strength layer, you'll very quickly get to no strength anyway. So it really doesn't matter, if you take my point. I think that answers the question.
Yeah. Another question, what are the locally available fire resistance adhesives for glulam sections? And what is the acceptance criteria, and what does the NZBC, New Zealand Building Code, says in the aspect?
Okay, well, this is, as I mentioned before, it's slightly a grey area, because it's something which is evolving. But I will just tell you why it's evolved and how it's evolved, because so in New Zealand we have no standards for adhesives, and the manufacturing standards for glulam and LVL and CLT do not have requirements for adhesives. But I'll tell you why it's become important internationally. When cross-laminated timber, CLT, was really invented in Europe and made in Austria and Germany and Italy and widely used, and as long as you have thick, relatively thick layers, you can get a good fire resistance in a fire resistance test. But when in the US and Canada and North America, when CLT started becoming popular, the fire services said, oh, we're nervous about this, we're scared about it. Could you do a room fire test, please? And they did. They built a whole room with CLT walls and floors and ceiling and doors and windows and lit the fire. And the CLT behaved very well. And the fire grew like the curve I showed, and the fire started going out. And when the fire was nearly out, the glue got too hot and it let go. And so what happened is a whole layer of charred wood fell into the room, and it was like more fuel, and the fire took off again. And the fire services became very scared of this, and they basically said, we're not going to accept this product for high-rise buildings unless you have a fire-resistant adhesive. And that's why it's now become mandatory in North America. And all I can tell you is that the company Henkel, that make and sell most of the adhesive in New Zealand, they have a fire-resistant adhesive, which they now sell in North America, and they are introducing to Australia and New Zealand. And I can't answer for sure whether it's being used. All I know is that the New Zealand Australian manufacturers are looking into it, and they're using it in some of their products. I hope that answers the question.
Thank you, Andy. Another question, can you please comment on post-fire stability requirements for boundary walls?
I'll just say a very few words about that. There's nothing special about wood buildings for post-fire stability. Post-fire stability, let me say something here. The post-fire stability requirements in the New Zealand Building Code are much tougher than anywhere else in the world. It's not seen as a problem elsewhere in the world because of the fire service will get in and put the fire out or whatever. But the reason for it is really for safety of firefighters. And it all comes from tilt slab construction. If you think of industrial buildings with big concrete walls, there's a huge safety problem with those walls resisting the fire but falling outwards after the fire or during the fire. And that's why that we have requirements, some of which are in NZS 3101, the concrete standard, and some are in the C clauses. And so you can see what I'm saying is that doesn't really apply to timber buildings, except that some TAs may require it to be provided. And all I would say is I would enter into a discussion about what it is that's being required and why it's being required and what you're trying to achieve. And in some cases, you can achieve the post-fire stability just on the basis of a charring calculation. But in some cases you can't, but that's all I can say for now. It's a difficult question to answer, but in many cases I would say that if it's a lightweight building, a lightweight timber building, I think the requirements are excessive and I wouldn't waste too much time on it.
Okay.
I hope that helps.
Yeah. A question from Maria Grace from Invercargill City Council. Loving this presentation. Residential dwellings, interior lined with plywood. What's your take? Still suggesting sprinklers?
No, look, that's a good question, very interesting question. And I like it, but it's something I didn't say earlier in this talk. All of this work I'm talking about with fire safety of linings and fire safety of structure, this does not apply to single family homes, to houses. Because in your living room, you've got far more combustible stuff, all the solid petrol in the foam cushions of your sofa, and all sorts of other combustible stuff. So this stuff just doesn't apply. And if you have a fire in your house, you have smoke detectors, you're alerted to the fire, you get out. So that fire safety in timber buildings becomes a concern as the building gets taller. So for a 1, 2, 3-story building, I would say many of these, well, we have to follow the building code, but the building code requirements for fire do not apply to single family homes or to small apartment buildings. So let me just leave it there.
Okay. A question from Paul Milworski. For laminated product, there was discussion about the risk of delamination along glue lines and secondary flashover. Is there any more guidance available on this issue? Thank you.
Yeah, that's the same question I talked about before. I would, there's no specific guidance. I would talk to the supplier of your engineered wood product and ask them what kind of adhesive they're using. That's the simple answer.
Okay. Another question. There are a number of CLT solutions on the market. but there are also PLT products. What comparison between the two are you aware of in terms of performance?
No, good question. Good question. In my list of products, I talked about glulam and LVL, laminated veneer lumber, and CLT, cross-laminated timber. I did not mention parallel laminated timber. Some people call it PLT. And parallel laminated timber is often used for floors, floor panels. It's like a glulam beam tipped on its side. And so it's long panels, long and strong, but not very wide. That's what PLT is. But it's mass timber, it's solid wood, and essentially it's just going to behave in the same way as any other glued wood product. I would say that because your solid wood is glued vertically with no horizontal glue lines, there is no danger of a layer falling off. And so using fire-resistant adhesive is not so critical if you have parallel laminated timber. Okay,
last two questions. What's your view on using a steam system like Fog Maker, or a chemical system like Fire Pro in commercial buildings?
That's beyond my capability. I don't have no comment on that. Sorry.
Okay. The last question: what are thoughts on CAS1 for SH buildings where there is no requirement for fire resistance windows in upper story?
Well, look, that's a detail of the code clause, and the short answer is I don't know, because I don't know my expertise is in structural fire engineering, and I would say go and talk to your fire engineer. Sorry, I can't answer that question.
Well, that's all what we have, and we have answered all questions coming up from the audience. And at the end, I would once again thank Dr. Andy Buchanan for giving his time today to talk on fire engineering in timber structures. And Andy, thank you very much, and we would look forward to see you once again in future. And also, we are looking forward to see you all on the 3rd of June for the forthcoming third TDS webinar series. Thank you very much.